Now this is the first video for solving the examples where we like to assume the trial depth. Now that is given in depth to confirm span to depth ratio in close 9.4.4.1, and I will show this one in the next video the close. Now we need to assume the trial depth because we don't know what is the depth of the slab in our given loading. Now the trial depth generally assumed by using the tables. There is a tables that is generally created for I think lifters and controls. In our case, there are various options given here. In our case, two adjacent edge are discontinuous. I can show it to you which two adjacent edge are discontinuous. We are working on these slabs, so we have this edge and this edge are discontinuous. Please note these edge are continuous edge. So in our slab I have two adjacent edge discontinuous. If I'm talking about this slab, I would have this edge discontinuous. But we in our case this is this edge is discontinuous. Now so in this case we need to find Ly on Lx. Now what is Ly and what is Lx? Now the Australian standard has provided the definition of Ly and Lx. Now if you go back to the page number on this page here, on page number 24, you can find the definition of Lx. Lx is a shorter effective span of the slab supported on four sides, and Ly is the longer span of the slab supported on the four sides. So our slab is supported on the four sides. Slab is supported on the four sides. There is a beam here, beam here, beam here, so that is fine. So please note Lx is a shorter length, so that is 5,000. What I done, I think there is a 250 millimeters of each side, that is a center to center distance. So that is, if I want to take the distance, the clear distance, 250 take away here, 250 take away here, that's give me 500, because the width of the beam is 500. So 250 goes both sides, that will give me 500. That's similar here, that is 500. Ly is 250 is this width of the beam, so 250 on each sides, take away 500, give me 7,000 millimeter Ly. So if I take the ratio, 7,000 over 5,000 is 1.4. Now someone might say that, okay, how do we classify the one-way slab or two-way slab? It's given in the examples, but if you want to know whether it is one-way slab or two-way slab, there is a definition given. If it is a one-way slab, your Ly longer to the shorter length is 1.2. So Ly over Lx is 1.2, unless we classify that is a one-way slab. There is another bending one as well, but I think this is a geometric definition, so we can also classify here that is a two-way slabs. Now continue. Now this trial depth, I can go back how to use these tables here. That is very approximate one. So let's say, as I explained, we have two adjacent edge discontinuous, and Ly on Lx is 1.4. So we need, let's say, in between. Now in this case we can have G plus Q. I think I will show you these additions. If you are talking about, let's say, 3.4 and 4.7, which is almost 7. So we are in this almost range between LAX 27 and 38. So if you just take it approximately between here, you can assume that is ln x over d equal to 29. Okay, so this is just assumptions. You can avoid these steps. You can assume d equal to 100 millimeter, 120 millimeter, 150 millimeter, 170 millimeter, or 200 millimeter. We done this example, so I know this trial depth, but in the real world we do have an Excel sheet. We will do the trial and error methods to come up with this 170 millimeter. But with the experience, we develop the skills to assume this trial depth. But this is a good starting point that we can assume this 170 millimeters trial depth. Now the dead load, I think some details are given in our questions. If you have this depth, so the density of the concrete given 25 times the thickness of the slab will give me the kilopascals, that is the weight of the slab in kilopascals, plus there is 0.5, they allow on 0.5 is to be made for partition. So the partitions is 0.5 kilopascal. So if I add these together, I would have a dead load of 4. I would have a dead load of 4.7 kilopascals. Now the live load is given in the questions. Imposed live load is 3 kilopascals, that is written here. Now in the question it says that design for corner slab for the uniform, but if in case the question does not say that which one is going, so we need to find the critical slabs. Critical slab means which one going to have more deflections. So if you're talking about this, let's say this corner, and if you compare these two slabs, now this slab here has a 3 continuous edge, meaning this edge are continuously supported. Only one discontinuous edge, meaning that this slab will deflect less under the same loading conditions. You can imagine that this slab will going to deflect less, because this has a larger deflections here when you compare these two. Again this has the same deflection, but if you compare again this one, so the critical slab will be your governing slab is your corner one. That's what the example is saying, that okay, design for corner one. Once this depth is satisfy the corner one, which is the largest deflections, this definitely going to satisfy for this slab. So we are not going to make the check for these ones, but I put the notes here for uniform slab thickness. That question is asking, and as all the slab have the same dimensions, you can see this 7.5 meter by 5.5, 7.5, 5.5, 7.5, 5.5. so all the slab has the same dimensions. The corner panel with the adjacent edge, this condition will have the greatest deflection. So this will have a greater deflection, this will have greatest deflection, this will has a larger deflection, this will have a larger deflection compared to these two. So our design will go on by these two corner ones, 4 corner one, but we are working on this one for this. In the next video, that's what covered. In the next video I will continue solving this example. Thank you.